I am so sorry I couldn't be halfway around the world to join you. But yeah, getting to Boston and back on the weekend was not something that I could commit to. But I did have to, be here in spirit at least, or present something. So here's what it's going to look like. All right. We're going to talk about assumed knowledge. I'm going to race through that pretty fast. And so you can leave during that point if you go, I do not have any of that assumed knowledge. We're going to talk about choosing size limits. We're going to talk about choosing time limits. We're going to go into the details, by which I'm going to throw a few URLs at you for further reading. And then we're going to talk about all the things to do beyond what has been done. Okay, so here's your assumed knowledge. Bitcoin has a stack-based scripting language inside it. Much of this was truncated in 2010 as a result of the CVE discovering its unfathomed power, I guess. So the resulting half script severely limits the expressibility of what you can do with your programmable money. And undoing it, restoring the 2010 script things, particularly OpCat, but a few others could actually do this, would give you back some covenant ability, although terribly badly. Okay, so that's my kind of assumed knowledge. I assume that we all are familiar with that. If not, you've heard it now. So let's look at the limits in 0.3.0 back in 2010. This is not quite true, but it's pretty close. You had add, you had multiply, you had cat, which everyone loves, concatenating two things together. You had invert, you had left shift. You had individual stack elements, and none of these really had any limits. I mean, there were actual limits, but no reasonable limits, and that was part of the problem, right? You could write a script that would consume, infinite resources. So Satoshi went through 0.3.1 was released, and a whole heap of things got cut down. Op-add in particular got cut down to 4 bytes, 31 bits for you, or 32 bits with a sign bit. Multiply basically got cut down to 0. It's called op-drop now. Cat, invert, left shift. I mean, they all got, I put 0 here because they were all eliminated entirely. And the stack element size of 520 bytes was introduced. So you can't have more than 520 bytes in the stack. And any opcode that could make it bigger had been disabled anyway. So if we're looking at this, right, what would we want? Right? We can solve for Bitcoin. We would like some of that back. What are some good numbers? Well, arithmetic. It'd be nice to have more than 31 bits of arithmetic, particularly, if you own more than 21 Bitcoin and you want to write a covenant or something. It would be nice to have full 64 bits. People suggested this. We should have some 64-bit opcodes. It'd be good to have mole back. When we look at that, there are a couple of problems. Just starting there. I personally have been through 16-bit, 32-bit, and 64-bit computing. So when you tell me, no, the 64 bits is, going to be enough forever, we're good. I color me a little bit skeptical, particularly when it comes to multiply, because you multiply, of course, two 64-bit numbers, you get a 128-bit number. So it's not entirely clear to me that just going, well, let's go from 4 to 8 is enough. And the other problem that you have then is, what do you do on overflow, right? What if you do go more than, your 8 bytes, your 8 bits, yes, your 8 bytes, your 64 bits. What happens if you go over? What happens if you multiply two numbers? What happens to go over? The element solution to this is to push two things on the stack. You push the result, but you also push a flag to say whether it succeeded or not. That seems really awkward because it basically means almost everyone will immediately follow every math operation with like a op verify or something. So when we look then at like cat, that 520 byte limit, for example, to move on to that one, starts to seem particularly limiting. That's because if you're using it to construct scripts, cat itself makes scripts more interesting. So you're actually much more likely than you are today to go, 520 bytes is actually not that much script. I want to do something longer. And so in general, in fact, I'm quite suspicious of arbitrary limits if we can avoid them. 520 bytes itself was an arbitrary limit, for example. So the right answer from an engineering point of view is big enough to do what you need to do. right? So enough in this case could arguably be one transaction worth. And how big is that? Well, that's less than 4 megabytes. So that kind of seems like a natural limit, right? Not so much an introduced one. That's a lot more than 520 bytes. But is it reasonable? Well, 4 megabytes isn't much these days, right? Nobody is within 4 megabytes of their Bitcoin D failing to process blocks. But we're allowed 1,000 stack elements. And 4 gigabytes is not so obviously reasonable to demand of Bitcoin block processing. So a reasonable compromise on top of this is to go, okay, well, in a stack-based language, you need to duplicate things to do anything. That's kind of how it works. So you can have a total of 8 megabytes on stack. And any individual element could be 4 megabytes, right? So happy engineers, right? We've increased the limits, restored the opcodes. Memory consumption is still very, very reasonable, peaking at like 12 megabytes-ish per block. Okay, great. Well, once you do this and you start looking at this, a new concern emerges, right? How slow can things get, right? Let's look at the obvious case, like SHA-256. Hashing 520 bytes on the machine that I'm presenting on now takes about 590 nanoseconds, right? So we don't worry about it too much. But hashing 4 megabytes on my laptop takes about 3.74 milliseconds, which is great. We've obviously optimized SHA-256 a lot. We do a lot of hashing in Bitcoin. But when you start to realize that in a block, you could have to do perhaps within enough scripting, almost 1 million of those, that number starts to look pretty big. Upmul is even worse. If we multiply 2 megabyte numbers, hitting our stack limit of 4 megabytes, and we use like a fairly simplistic implementation of school book multiplication, that takes 163 seconds on my laptop. Okay. Now, that is a fairly simplistic implementation. So if you look at a serious library that does multiplication, for example, libgmp, it does it in 55 milliseconds, which is proof that magic exists and wizards live among us. But even if we were happy pulling that in or re-implementing libgmp to do all the multiplication cases, it still doesn't solve the problem that we could have to be forced to do almost 1 million of these in a block. Right? So what do? Well, we already kind of have this issue in Bitcoin today. Right? We have opchecksig, which can be computationally expensive. And the solution for this is basically to have a SIGOPS budget based on weight. So the question then becomes, okay, can we use a similar thing for these other ops that could be slow, right? For things that can take huge variable length data on the stack. Okay. So this is what I call var ops, because I'm not good at naming things. And I have kind of 4 idealized goals that you would want from such a thing, right? Firstly, it constrains the worst case to no slower than it is today, right? And not some exotic slower, but some reasonable. If your machine's this fast, it's not going to get worse. It should be simple. I mean, simple is relative, but that's always a goal, that the system should be as simple as possible. Real code should provably never hit the limit. Now, this works really well for opchecksig, for example, because for every 50 bytes plus of witness data, you get another checksig, right? Plus, you always get one anyway. And it's pretty easy to show mathematically that if you're using normal signatures and doing normal things, you can't hit the limit, right? And that's not going to happen. And it's future-proof, right? We shouldn't be too embarrassed in a generation by anything that we implement here. Okay, so let's start with something fairly simple, no slower than the worst case today. I chose for my benchmark of like how slow a machine is, the time that it takes to do 80,000 Schnorr signature checks, not the hashing, just the signature checks. That is the theoretical upper limit of how many sig checks you would have to do in a block today. And here are the numbers, right? The Raspberry Pi 3 clocking in at 26.7 seconds to validate that. The Pi 5, obviously faster. My laptop features in here again, just under 5 seconds. And my 3-year-old build machine comes in at 2.5 seconds. So there's kind of our benchmark upper bounds, right? We don't want to make it any slower than that. Okay. Oh, Oh, I was supposed to flash those in one at a time, so you got the early preview. There we go. Okay, so there's our benchmark. Now, simple. Well, there are various forms of simple, right? But one simple win is, in fact, to switch to unsigned numbers. Um, Signed numbers, which are inherited from the use of OpenSSL's big num library, were mixed quite badly when you've got variable length numbers with a sign bit and bit operations and things like that. The intersection of those is pretty poor. In particular, you end up with a -0 value, which is kind of fun. So then you go, well, what do you do if you subtract and you underflow? Well, you simply make it fail, because usually that's not what you want. And you can always check beforehand if you want to do something else. Divide, of course, should fail on divide by 0. Add and multiply don't really fail because they don't use any more, they don't use any more stack space. But of course, they can go over 4 megabytes. So if your individual goes over 4 megabytes, because you could have 8 megabytes to start with, you could fail that way. And of course, we define arithmetic ops to trim zeros. Trim zeros at the end because we're little endian here. So a little bit counterintuitive. Okay, now I'm going to quote from the draft bit, for example, that basically every opcode can be expressed, is most naturally expressed, and is implemented pretty much today as a linear pass across data, right? So it makes sense to cost it, and that's what we're here for. Based on the stack inputs or occasionally the outputs, things like left shift, obviously. What matters more is how big the output is, because we're moving the whole thing down. And so we make some assumptions that allocations and manipulating the stack vector itself, adding a new element to the stack vector and stuff is in the noise. It's kind of constant-ish time. And we assume that you're doing a simple linear thing. Now, you can get faster than this. There's nothing wrong, and it says this in the BIP. If you want to get faster than this, that's great, as long as you don't make the worst case worse. That's fine. And my second BIP quote basically tells you how we cost things. I spent a long time benchmarking things, had a whole heap of different theories, but in practice, it came down to 3 things. Some operations are basically pretty fast, very well optimized. Comparing bytes, copying bytes, and zeroing bytes. And so I went, right, they're worth 1. They cost you 1 budget per byte. Hashing, most expensive, SHA-256. 10 units per byte. And everything else is defined as a slow op, right? Which is 2 units per byte. Okay, so let's take some examples. Let's look at opt-up, right? Well, that's a copy. So 1 var op per byte. Op invert, well, it's a slow operation. You got to go through and do some, pull everything into a register, do something, tweak it back out. 2 vars per byte. Op sub, similar, slow, 2 vars per byte. Op add, okay. It's slow, so you have to do it. But then there's a case where you overflow, right? And if you overflow, you may go, oh, we don't actually have room for this number anymore. We got to reallocate and make a copy. So that's actually 3 var ops per byte. Op or is slow, and op or really only has to do the shorter operand, because if you're orating a long thing with a short thing, then the tail of the long thing doesn't change at all. So you've only got to go through the short thing. So it's twice the the length of the shorter operand. Now, op and is different. You've got to go through both of them, and then you got to zero out the rest if one of them is shorter than the other. But zeroing is fast, and it turns out that works out to the sum of the operand lengths for your costs. Okay, so we've described how you use budget, but what should our budget be? What's a reasonable number, right? Well, we said we've got our worst case numbers. So we take our various platforms. We go, cool, let's measure how long it takes to do one of these fast ops, one of these slow ops, one of these hashes. Choose the most expensive, right? What does it really suck at? Cool. Take that case and go, well, how many of those operations could you do in the same time as that machine can do 80,000 SIG-ops, which is our ceiling, right? And then divide that by 4 million to go, there's your budget per byte. Okay, and when we do this, we get numbers like this, my Pi 3. And just to be fair, I went only down to the Pi 3, not to the Pi 2, because it's a 64-bit machine. The Pi 3 is small and nasty enough that you can't actually compile Bitcoin Core on the Pi 3. Had to compile it on the Pi 5 and copy the binaries across, right? It is right at the bottom end. But it managed a VAROPS budget per byte of 6,415, which is not too bad. Pi 5, much higher budget. My laptop, similarly, 11,000. My build machine, 87,000. But remember, that doesn't have much budget because it was really fast hashing, right? So it only had 2.5 seconds to do that. Okay, cool. So we should take these numbers and go, okay, there's some reasonable consistency across there. And we should be even more conservative. So my draft answer is every byte of weight of the transaction gives you 5,200 VAROPS budget. Okay. Which brings us to the next thing. This idea that you want to show that you'll never hit the limit and have some convincing arguments for why you'd never hit the limit. Well, 5,200 means that an OP-SHA 256 opcode itself can pay for hashing 520 bytes, right? Because it's 10 VAROPS per byte. So that, off the bat, being the most expensive opcode already, shows that you can't exhaust the budget if you stick to current stack sizes, right? There's just no way. Okay. So that's nice, right? Things are not going to get worse from that point of view. It's not going to get more restrictive. Well, let's look at something more complicated, opmul, right? This is the cost for opmul because it does multiple passes. You end up with a number like this. If you want to do a 64-bit number multiply, so you push a number on the stack, call opmul, you can pay for almost 1040 bytes in just the opmul itself, not the number that you push, which gives you even more. So you can multiply some pretty big numbers without ever having to worry about budget. Opdiv, similar, opmod. The answer is 127 bytes. You end up with this formula. You go, cool. The opdiv itself, the weight of the actual operand, will give you a 127 byte divide by a 64-bit number. So that's pretty good. So it does turn out it's actually really hard to hit these limits, right? So I wrote a quick tool that, given a script, will tell you what limit could you hit, and you go, cool. What happens if you give it op-add, right? This is in the repository, and it goes worst case if you feed it. The thing is that the bigger witness budget you give it, the bigger witness you give it, the higher its budget gets too. So you feed it a 4 megabyte input, which of course can't actually happen, but that's our nominal ceiling. It still only uses like 0.05% of its budget that it gets. Opmul does. You could feed two things into opmul, and the cost of the opmul climbs faster than the extra budget you gain from having bigger things as your inputs. So that tops out about 10,000. But if you're trying to opmul by some random, 64-bit value, right? You can't find something big enough. You can't exhaust your budget on that one. So if you're multiplying by any fixed size, and even, I tried to give it a push that was big enough to use up the budget, and there you can see me producing 10,000 byte pushed. And opmul, and that gets close. That gets 95%. So if you're multiplying things by 10,000 byte values, then you're going to be able to hit the budget. Now this tool doesn't fully evaluate, but it does actually overestimate costs in a number of cases. But you can take a given script and reasonably prove that it cannot go over budget with that. Okay. Okay. So I haven't managed to prove that you can't hit the limit, but I can say that you probably won't hit the limit in reasonable cases. And for given scripts, you can certainly show that that you're good. Okay, now future proof. Okay, well, it's tempting to count on improvements and make the budget extremely optimistic, but my experience so far shows me that this is basically being unnecessary. Sure, computers will get faster, I assume, but as long as they don't get slower, these limits are pretty good. And of course, we could optimize things. We could totally make things better. And in a future software, potentially we go, cool, actually, we way overcharge for this because it turns out everyone's doing it this way and that's way more efficient. That's great. But we simply don't have to. The budget's really, really high. Okay. Unfortunately, in half our presentation, I don't have a huge amount of time to step through exact things. But I love conference-driven development. Last week, I spent polishing my draft BIP and hacking up my hacked Bitcoin D, which just interprets what it calls Taproot v2 and enforces the limits and has a pile of benchmarking code in there. So there is stuff to do. Okay, But there is a whole pile of further work. I've done a lot of benchmarking and figured out something that I think is a reasonable model for how we can do operations. But I implemented all those new opcodes. We should probably test them, right? We should check they work as expected. We should some of the existing opcodes were modified slightly. That should also be checked. For example, actually, I'll get to that in a second. And of course, lots of test vectors, right? You want to write a BIP, you got to have a lot of test vectors. This will fail, this will work. This limit will be this, right? Code review, always good. C++ is a fun language. In particular, there are a number of cases where we were transparently and not to my eyes, obviously, copying things on the stack internally. Now, that doesn't matter when you got 520 bytes, but when you start throwing around 4 megabytes at a time, internal copies in C++ code can start to really add up. It was confusing some of my benchmarking work for a while before I realized it, actually, because I was benchmarking the interpreter itself. And it was, in fact, doing copies of stack elements unnecessarily. So, finding unexpected stack copies is kind of a sport. Certainly, there would be a way to modify the code to actually flag those if they happen, but I have not done that. And of course, BIP review, right? There's a whole pile of things in the BIP that have been left for people to bike shed, right? Should we charge for all pushes? We currently, certain opcodes that care say, hey, you charge for this, but we don't charge, for example, we don't charge for pushing a true or false value on the stack in many opcodes, right? Should we? For consistency, should we got every stack operation, we'll charge you 1 for this or something? That's something we could certainly bike shed. Should we roll SIGOPS into VAROPS, right? We have the SIGOPS limit. We could just express that as VAROPS limit and be done. I have not done that in my practice implementation, but the BIP says that we should. Maybe we should. Maybe they already exist. It's fine. And of course, the big one, how does this fit with any other proposals, right? How does this fit with introspection opcodes? If you have this, what do you do with your introspection and all those things? And there's a whole rabbit hole there that I'm not even going to touch. Of course, deployment. What other opcodes? What other things should go in with it, right? What makes sense? I said you're going to get covenants badly. Might as well do them well, right? Do we want opchecksync from stack? I think everyone loves opchecksync from stack, probably. The checksync we deserve, perhaps. If we want to make Merkle trees, we probably want some kind of ability to do a tweak add. And for nasty reasons involving the fact we're Lendian and the Merkle compares are big endian effectively, we would probably want a byte reverse to make that possible, or make it easy. So, there's a whole pile of other things that we might want. And what does it actually look like? Is this BTC1Z? That would be the next Bech32 letter. Do we do 33 byte pub keys? Do we return to those? Do we get rid of 32 byte pub keys? Do we remove the requirement to have an explicit key? This is one of my things. I think there are a number of cases where that useless key could just be implied, and we could not have to do that. So, if you really are, it's a script. It's obvious it's a script. You're always going to know it's a script. I think that space savings become important, and I think that might be nice to have. Of course, benchmarking is really good. I mean, worst case in various machines, I did benchmark a whole pile of different variants trying to find out, exactly what bit patterns were slowest for add and stuff like that. Can you find a machine that sucked worse than my Pi 3? That's a good question. And importantly, the critical one for this is, can you find any cases which perform worse than expected? We've got a fair bit of headroom in there, but it's worth going through that and going, hey, I can prove that all these ops perform in line with or far better than we expect from the model. Okay, and I have tried to leave like a 1 minute at least for questions, if there are any.
Any questions? We got 2 questions.
Did you say, thanks for your talk, by the way, did you say that you wanted to make a Taproot version, SegWit version 2? Why not just TapScript version N?
No, I left that absolutely open to bike shedding. We totally could do it either way, all right? It depends what other changes we want to roll in.
And one more. Oh, actually, same question.
Great,
Rusty.
Okay. Great.
Thank you for your time. We're going to actually try to keep you on the stream. and we're going to have you on the panel in about 15 minutes. For now, everyone can go take a break, and then we're going to have BitScript doing a little educational thing in between.